Swayam Prabha. Digital India. Educated India.
In this case, if we do the determinant of all these matrices and if we find that each of the principal determinant is positive, then we can say the matrix is a positive definite matrix. In order to define whether a matrix is a negative definite, we have to find the principal determinant of the negative matrix, which is minus A, and if we find that all the principal determinants are positive for this negative matrix, then we can say A is a negative definite matrix. These are the two ways how we can find out a matrix is a positive definite or negative definite. There are other ways. You can adopt one of the way to identify. In this class, we'll mainly adopt the principal determinants as it is easy to calculate. In the optimality condition, we said there is a situation when the Hessian matrix is neither positive nor negative definite. In that case, we know that we have reached to a point of inflection or a saddle point. So let's look into what is this saddle point. So here is a function of two variables x and y represented as x square minus y square. And if we plot this for various values of x and y, we'll see that there is a point here. From this point, if we try to move in this direction, the function values are increasing. Same thing is happening in this direction. However, if we move in this direction, the function values are reducing, and the other side also reducing. It looks like a horse saddle, and the point at the center where slope is expected to be 0 is not actually yielding a minimum or the maximum point, because if we move in any direction, the values are either reducing or increasing, and we cannot say for definite that we have either reached a minimum point or the maximum point. Now let's look into one of the problem, how we can use the first order derivative and the second order derivative to find out the optimum point. In this example, we have two variables x1 and x2, and the function looks like this. We need to find out whether we have an optimal value at certain point or not, and in the process, first we need to identify the points that meet the necessary condition. For that purpose, we have to do the first order derivative, and once we do the first order derivative, we can equate it to 0 and find out those points. So the first order derivative of the function with respect to the first variable, which is x1, can be written as this way, and if we equate it to 0, we can get two x1 values. One is x1 is equal to 0, or x1 is going to be negative 4 by 3. Now the same function, if we do the partial derivation with respect to the second variable x2, we can get this function, which we equate to 0, we'll get x2 value as either 0 or negative 8 by 3. We know these are the 2 points for x1 and these are the 2 points for x2 where the slope is going to be 0. So the combination of these 2 points of x1 and x2 would yield the locations where slope is expected to be 0. So those combinations are going to be the possible decision variable values, and these values are 0, 0, 0, negative 8 by 3, negative 4 by 3, 0, and negative 4 by 3 and negative 8 by 3. We need to check the sufficiency condition for all the 4 points to decide or to conclude if these points are going to yield the minimum or maximum or a saddle point. So let's move on to the sufficiency condition. For the sufficiency condition, we have to find out the Hessian matrix. So the Hessian matrix, if we do the double derivative of this, we can say double derivative with respect to first, if we do it with respect to x1 is going to yield 6x1 plus 4. If we do the double derivative with respect to x1 and x2, we are going to get 0. Likewise, the second term, if we do the double derivative with respect to first x2 and then x1 is to yield 0. If we have done the double derivative with respect to x2, then it would have yielded 6x2 plus 8. So we can use this to come up with our Hessian matrix. So now let's look into the Hessian matrix, which represent the second order derivative of the objective function. The Hessian matrix is going to look like this, and if we want to find out whether it is a positive definite or negative definite or indefinite, we need to find out the principal determinants and see whether those represent the positive definite matrix, negative definite matrix or indefinite. So the principal determinants of the Hessian matrix, one is this, the second one is this. We have 4 points, and in the 4 points, let's check the principal determinants one by one. The first point, which is 0, 0, if we check the principal determinant, the first value is positive 4, the second is positive 32, and this indicates the matrix is positive definite. So this point 0, 0 is going to represent a relative minimum, and if we find out the function value, we'll see that the function value is 0. The second point, which is 0, negative 8 by 3, we'll find the first principal determinant is positive 4, the second one is negative 32, and we'll see it is indefinite, which indicates that we have reached a saddle point and the function value is this. The third point is negative 4 by 3, 0. At this point, if we see the first principal determinant is negative 4, the second one is negative 32, and this is again indefinite, indicating a saddle point with a function value of 32 by 27. The fourth point, negative 4 by 3 and negative 8 by 3, is going to yield the first principal determinant as negative 4, the second one as positive 32, and if we look into the characteristics, we'll find out that this is indicating a negative definite matrix, and a negative definite matrix is going to represent a relative maximum point, and the value at that point is 32 by 3. So we got 2 points where we have reached a saddle point, and we got 2 points, one of which is yielding the minimum point and the other is yielding the maximum point. So let's look into the graphical representation of the point. So we had the 4 possible variable value. If we plot the function and see where it lies, the maximum point lies here, the minimum point lies here. The saddle points are somewhere here, and the other point, saddle point, is here. So it is very clear the 2 saddle point, if we go in different direction, we don't have a definite way of saying it is a minimum or maximum. So again, this point, if we show if the function value is reducing, if we go in this direction, the function value are increasing. So these two are the saddle point. If we look into this point, whichever direction we go, we see that the function value is reducing. So this is my maximum. And if we look into this point, whichever direction we go, the function values are increasing. So this is my minimum.
So in today's lecture, we discussed about the unconstrained multivariable optimization problem and the classical method of solving the unconstrained multivariable optimization problem. In the process, we also saw how we can use the first order partial derivative of the objective function to come up with the necessary conditions which yielded the potential points where we may obtain the optimum solution. Using these potential points, we looked into the sufficiency conditions, and in the sufficiency conditions, we did the second order partial derivative of the objective function. However, while concluding, we indicated that the second order partial derivative of the objective function may not be sufficient in certain cases, particularly if the Hessian matrix is semi-definite, and in that case we have to look for the higher order derivative of the objective function. The second order partial derivative of the objective function already yielded a two-dimensional matrix. Solving the higher order partial derivative of the objective function can lead to a complex tensor which might be difficult to solve manually. Hence, to use the classical method to solve unconstrained multivariable optimization problem, we would like to limit the process up to the second order partial derivative of the objective function. Now, all this we had discussed for the objective function without any constraint. There are many instances when you have to comply to the constraints of the engineering problem. In that case, the problem will become constraint multivariable optimization problem. And in the next class, we will start discussing about the constraint multivariable optimization problem. That's all for today. Thank you and see you in the next class.